All right, ladies and gentlemen, this is asynchronous day. This is a review of all the 3 laws so you can get ready for doing the test. So inertia is also the first law of motion. Inertia is a property of matter. It's not a force. It's just something that exists with anything that has mass. And inertia is an object's resistance to change in motion. Think about it as resistance is, I don't want to do this, right? So you might have resistance to doing homework. You might have resistance to doing chores. So inertia is kind of like that. It's like everything inside of it that because of its mass will just keep wanting to not want to stop or not want to go. So the tendency of an object with the mass to resist change in motion. So here is me flipping a coin on a index, well, actually my license plate, my license, driver's license, and the coin stays still. And there I go, click it, and the coin, because it resists change in motion, right? Object rests, stays at rest. Object in constant velocity, the direction is the same. The speed is direction in the same direction. Reminder, only 2 states. Balanced forces are balanced because, if you think about it, a balanced force looks like the arrows or the force vectors are the same. In this, there's a balanced force, no acceleration. So if I were to draw a box here, not very good at drawing this box, and if I took an arrow, here is an arrow going to the left, and here is an arrow going to the right, and I'm trying to make them the same length. So this is a balanced force. This will stay at rest, zero motion, or a balanced force that looks like this will keep it moving in a constant velocity. There's no net force. Now, when we talk about a force that has a net force, so let's do the same thing, but now I have a really long force arrow going to the left and a really small arrow going to the right. So the net force would be, this cancels out a little part of this, but it's still going to go to the left. All right, so what is inertia? The amount of mass determines the inertia. Objects want to continue doing what they're already doing. Objects with less mass have less inertia. So a small rock, you can throw that, skip that stone pretty well. Objects with more mass have a lot of inertia, harder to change. And that really makes sense. We've experienced that, but we've never called it inertia. So let's just kind of review again the law of motion. An object at rest stays at rest. An object in motion stays in motion unless an unbalanced force acts on it. Remember, on the Earth, we have a lot of unbalanced forces. We have friction, like you kick a ball, the friction of the grass will slow it down. You will also, air resistance will slow things down. But in space, when it's frictionless, right, it keeps going. So here is a soccer ball being kicked. There's the unbalanced force. The object will remain in motion and constant velocity in a straight line unless we get an unbalanced force. And again, the grass will slow it down, the air resistance will slow it down, but in space, we don't. So objects at rest stay at rest. So here again is my force vectors. So this person's pushing with the same force as this person. And if I draw the arrows, hopefully I draw them the same. So this is 0. It's balanced force. Here is an unbalanced force. So of course it's going to go in this direction. So this has a net force to the left. All right, so is a force needed to keep an object in motion? No, the object in motion stays in constant motion, velocity forever, because this is frictionless, right? I'll keep my orbit around the Earth. So what property of an object described as a tendency to resist acceleration? So remember, it's a property, not a force, because if you have inertia, everybody has mass, it has inertia. Resistance to accelerate, resistance to change from rest. Which of these two statements below inertia true? Inertia is the tendency of a stationary object to resist motion, and a natural tendency or property of the motion to resist change in velocity. Which of these is the qualities or the quantities described an object tendency to resist the state of motion? Now that's the mass of the object. The size of an object doesn't matter, but the mass. Okay, so the more mass it has, okay, because we add gravity to that, adds weight to it. So we can also say weight, but you can have mass in space. That's why we have to use that word mass. All right, let's look at Newton's second law. This law says that there is a relationship between acceleration and the mass. So, which ball requires a larger unbalanced force to accelerate? Of course, you would have the golf ball, right? The golf ball would have more mass, and it has more. It takes more force to accelerate it. The ping pong ball less, right? All right. So let's take a look at this acceleration. So Newton's second law of motion says force equals. Okay, I'm writing all over the place here. Force equals ma. So when you've got the m and the a together, it's the same way as saying force is equal to mass times acceleration. So force is equal to mass times acceleration. So that's an algebra thing. So here's the equation. Force is equal to mass times acceleration. Heavier objects require a greater force to achieve the same acceleration as a lighter one. Okay, so again, if I have some barbells, if I would to try to throw some barbells, right, that weigh 10 pounds, right? If I want to get, let's say, I want to get a force to make this to be 20 newtons. Okay, I want to put a 20 Newton force on this. I can get this to accelerate at 2 meters per second squared, right? All right, so if I want 20 newtons of force, and if I only have 1 pound, right, well, they usually use kilograms, I can get that to go to 20 meters per second squared. I can really accelerate that with the same amount of force. I can really get that going very fast with the same amount of force. So the greater the heavier the object, or the more mass an object has, the less I can, it takes a lot more to speed it up. If I wanted to get this to get to 20 meters per second, okay, so 10 times 20 meters per second, I got to put 200 newtons of force on there in order to do that. So that's an awful lot of effort. So the acceleration of object is directly proportional to the force. Okay, so the more force, let me put that, more force, the more acceleration, right? So that's what they mean by directly proportional, right? Inversely to proportional, the more force, the less it would go in opposite direction. So this is proportional. So it makes sense too. Again, we just don't use those words directly proportional when we talk about force. We talk about how it increases. If we increase the force, we can make it go faster. So which kart requires more force to have the same acceleration? Of course, the one that has more things in it, right? More, it's heavier. It's got more. If you push a cart at a force of 10 newtons, Cart 2 is pushed with a cart. Okay, so let's take a look at this. So let's pretend that they both have a mass of 5 kilograms. All right, both of these are empty, right? And if I get a force of 10 newtons equals 5 kilograms, I'm using that force is equal to mass times acceleration, right? Cart 1 is pushed with a force of 10 newtons times 2 meters per second squared would give me 10 newtons. And then cart number 2 is 40 newtons, still has the same mass, it's 5 kilograms. So times 8 meters per second squared. So of course this is going to go faster. The greater the force, the faster. When the mass remains constant, more force means more acceleration. When the mass remains constant, less force means less acceleration. You can see that in the Hulk pushing something versus a little kid, less acceleration because they can't push as much force. So suppose a student pushes a cart with 40 kilogram mass. How much force is needed? So here is my givens. Okay, so I've got 40 kilograms. Ag, that's my mass. And then I have acceleration, 2.5 meters per second squared. That's my A. My formula says force. I'm going to show you this. Triangle, force, mass, and acceleration. So I'm looking at the force. I've covered that up. It says they're side by side. So I'm going to put times, plug this in, 40 kilograms times, put a dot instead of an X, 2.5. So 80 plus half of that is 100 newtons. Final answer, 100 newtons. A dog has a mass of 220. Okay, so it's given. We have the mass. We're going to use the formula F equals ma, but then we're going to use this triangle, right? Force, mass, and acceleration. So we have the mass of 220. We have a force of 40 newtons. So what's the acceleration? So we cover up the acceleration, and we've got force divided by mass. Okay, so force is 40. Oops. This is 40 newtons divided by 220. All right, my final answer, let me use my calculator here. So give me a second. Use my calculator. All right, so 40, use the divide by 220. So 0.18181818, so it kind of repeats. Point acceleration is equal to 0.1, I'm going to make this 18 meters per second squared. All right, so for third one here we have Newton's third law in review. I understand the law for every action there is an equal and opposite reaction. Know that action and reaction forces are different on different objects and therefore cannot cancel each other out. And we'll talk about that more next week. So what does Newton's third law of motion say? Objects in motion. Nope. For every action, so this is supposed to be letter C. I didn't get it real well here. For every action, there is an equal and opposite reaction. So that's how things move. Right? In Newton's third law, how does forces between interacting objects describe? They're equal in magnitude and opposite in direction. Not sure why this shifted on me. Equal in magnitude and opposite in direction. So if we look at this, looks like A and B are pushing on each other, and the force vectors are the same. Now here, it looks like they're not the same here, but if we look at this, right? So let's say that on the left-hand side, the force, all right, so this is 20 kilograms times 2 meters per second squared, right? So that gives me a force vector of 40 newtons. On this side, we have 40 kilograms, because we have 2 people, times, and you notice the acceleration is slower, 1 meter per second squared equals 40 again. So the arrows, if I were to show the arrows here, the arrows would be the same, just that the acceleration is different. Forces are equal and opposite, third law, but the person with a smaller mass will experience a greater acceleration. So which of these is the action? Remember, there's an action force and a reaction force, right? So the blue arrow in this particular case is my action coming from gravity, the book being placed here, right? Notice that they're equal and opposite, right? They're the same length, equal and opposite. This is the supporting force, right? And the supporting force is called the normal. Not sure why. I'll have to do some research on that. So the normal force is a supporting force, and they're on 2 different objects. So the normal is pushing up, and the gravitational force is pushing down. All right, so which force is greater? They are both the same. And you can see that by the length, and they always will be the action reaction forces will always be the same. So in the top picture, Kent Budget is pulling a rope that's attached to a wall. In the picture, Kent is pulling upon the rope attached to an elephant. In each case, the force scale shows 500 Newton. Kent is pulling the same force in each case, so he's pulling out 500 Newtons and the wall is pulling back at 500 Newtons. You substitute the elephant in here, the elephant is pulling back with 500 Newtons. So equal and opposite. Okay, so that's what I have for you as far as review goes. Thank you for listening, ladies and gentlemen. You do the assignments that are scheduled for you, and we've got this recording for less than 30 minutes. Thanks a lot.